Good morning. Today we are going to discuss what is minimal cover. Already we have discussed what are equivalents of functional dependencies, set of functional dependencies, and now we are going to have this. We are going to discuss minimal cover. The definition of minimal cover is minimal cover for a set of functional dependencies E is another set of functional dependencies. That means from the given set of functional dependencies, you are going to find out another set of functional dependencies F that satisfies the property that every dependency in E is in the closure of F plus. That means all the dependencies are preserved and it is a minimal set compared to the original one. That means the minimal cover you are going to find out. It must satisfy the following condition. Every dependency in F has a single attribute on the right hand side of each functional dependency. That means by reflexivity, you can decompose. By decomposition rule, if you have a functional dependency, say A determines BC or A gives BC, you can split that into A derives B and A derives C. That means, first of all, what you have to do is the right hand side of every functional dependency should have only a single attribute. Okay, then we cannot replace x determines a of y determines a if y is a proper subset of x and still have a set of functional dependencies that is equivalent to f. That we will discuss. We cannot remove any dependency from f and still have a set of dependencies that is equivalent to f. We can choose the minimal cover as the set with minimal number of functional dependencies. So those points you should be aware of. You will be aware of all these things once you do, or how a minimal set of functional dependencies, or how minimal cover can be generated with the help of two examples. This is example number 1 and this is example number 2. In example number 1, we have A determines B, C determines B, D determines A, B, C, and AC determines D. So I am going to write those. A determines B. Here, first rule we are going to apply. That means every dependency in F has a single attribute on the right hand side of each functional dependency. So A determines B. There is no. That means that is obeying this rule. That is obeying the rule. That means right hand side is having only a single attribute. C determines B. That is also satisfying this property. But you have D determines ABC. D determines ABC has three attributes on the right hand side. So I am going to split that like D determines A, D determines B, and D determines C. That means I am going to have D determines A, D determines B, D determines C, and the last one is AC determines D. AC determines D. So these are that means after the first step, I have split this D determines ABC into 3 and all others are having only a single attribute on the right hand side. So after the first step, these are the set of functional dependencies. Okay. Now the order is very important. From the start, we are going to check whether this A determines B or C determines C. If we are going to check whether this can be removed from the set. So for that, we are going to have a check. That means initially we are going to find out whether this A determines B can be removed. So for that, we are going to find out A plus. That means trivially A is in A plus, and from A you can reach. That means this is the closure of A you are going to find out. Closure of A. That means A plus is having A, that is trivial, and A determines B, so B has to be included here. Then B determines or AB, B or AB, that means here we are not having any subset of this AB here. We have to check whether any subset of AB is here. Now subset of AB is A, so B is added. Now subset of AB, nothing is there, so A plus is AB. Now what I am going to do is, after removing this A determines B, again if the closure of A contains AB, then that can be removed. So at this point in time, think that this A derives B is not there. So at that point in time, again you are going to find out, that means A plus, without this functional dependency, A determines B. Then this one returns A determines B on the left hand side. By trivial functional dependency, A plus includes A, and excluding this, we are not having any S here. So initially we are having the closure of A as AB, and after removing this A determines B from here, from the set of functional dependencies, your closure is having only A. That means this AB and A are different, so we cannot remove this A determines B, so that is not removed. Okay. Now again C, we are going to find out C plus equal to, by trivial functional dependency, C is there, C determines B, B has to be added. Then what about B? B is there, not there on the left hand side, C is on the left hand side, and here you have C, but A should also be there, so C determines B. C plus or closure of B is having only CB. Now after removing this C determines B, you are going to remove this. Suppose that this C determines B, it is not there, you are going to find out another closure of C. Trivially, this is including C, and suppose that this is not there, what will happen? It is only C. If you are removing this C determines B, closure of C is having only C, so this CB, closure of C plus, closure of C including C determines B is CB, and after removing that, the closure contains only C, so this can't be removed. So that is there in the minimal curve, that should be in the minimal curve. Now what about D determines A? You are going to find out the closure of D. By trivial functional dependency, D is there, then A, D determines A, B and C, D determines B, D determines C, so B, C, D, A, B, C, all A, B, C, D's are there for the closure of A. Now suppose that you are removing this, D determines A, then what will happen? Suppose that you are removing this A, again D is there, D determines B, B is there, D determines C, C is there, and DBC, any subset of DBC, this is not here. After removing this, you are finding out this, and now what about this? Any subset of DBC? C determines B, okay. D determines B, D determines C, and AC. A is not there, so the closure of T contains DBC only. Here we have DABC. These two are different, so there is no possibility of removing this. D determines A. Now what about this? That is D plus, before removing the closure of, this is DABC for all these three. Before removing either D derives B, D derives A, or D derives C, the closure of D is DABC. Now you are checking whether D derives B is redundant. So after removing this D derives B, I am going to find out the closure of this. Closure is this, that means D D and D derives B. We have removed this. So D derives A is there. D derives C is there. Now DAC. Now AC determines D. AC is here. AC determines D. So D already included. What about this? A determines B. A determines B means B is also included. So DACB. That means even if this is not present here, the closure of D remains the same. Closure of D remains the same. So the closure of D is DABC, and after removing this D determines B, again the closure is DACB. So this can be removed. Okay. Then what about D determines C? Again, you are going to find out. Once you have removed this, then now you have to check only these 5. 1, 2, 3, 4, and 5. This is no more. And now D plus is, now see again the closure of this is, what is this? D determines A, D determines C. That means A, C. Then AC determines D and A determines B. AC, DB. And after removing this D determines C, D determines C. Now again you are going to check. That means D is there. Then D determines A. A is there. So you have removed this D determines C. Now DA. So A determines B is there. DAB. DAB. Now A determines B. C determines B. D determines A. Now this D plus is having ACDB, and after removing this D determines C, this is only having D, A and B. So there is no possibility for removing this. Okay. Now AC determines D. You are finding out AC plus, which is AC. Then A determines B. C determines B. AC determines D. AC determines D. So after removing this AC determines D, you are finding out AC plus, which contains AC, and after that A determines B. A determines B and ACB. C determines B. ACB. That means AC plus, or after removing this AC determines D, you are having only ACB in the closure of AC plus. So there is no possibility for removing this. So you can remove this D determines B from the set of functional dependencies. That means now we have checked for right side redundancy. Now you have to check for redundancy on the left hand side. For that, you have to choose those functional dependencies which is having more than one attribute on the left hand side. So here you are having, that means you have removed this, and now you have A determines B, C determines B, D determines A, D determines C, and AC determines D. And now on the left hand side you are having a functional dependency which is having two attributes on the left hand side, and now from this you are going to find out whether this A can be removed from this production or C can be removed. Okay, then what is AC plus is AC BD. Now after removing this A, you are going to find out C plus. That means if this A can be removed, then the closure of C contains ACBD, ABCD, all those things, ACDB. That means if the closure of this, and after removing an attribute from this, again the closure remains the same, that attribute can be removed. Okay. So after removing A, what is C plus? This is C. Then C determines B, CB, and CB. Then nothing else. So the closure of AC is ACDB, and after removing this A, the closure of C is CB only. That means A cannot be removed. A can't be removed. What about C? Now we are going to check whether C can be removed. So for that, we are going to find out the closure of the remaining. That means A closure. What is A closure? A closure is A, B. A closure is trivially A, and A determines B, you have B. AB, nothing else. That means closure of AC and closure of A are different, so C also cannot be removed. So the minimal cover for this set of functional dependencies is A determines B, C determines B, D determines A, D determines C, and AC determines D. Okay. So now we are going to do the second example. Second example I am going to do. The functional dependencies are, this is the second example, B determines A, D determines A, and AB determines D. Okay, AB determines D. Here we have having only three functional dependencies, and step 1 is over actually. That means on the right hand side you have only a single attribute for every functional dependency. Right hand side is having only a single attribute. So step 1 is over. In step 2, we are going to check whether this can be removed. B determines A. What is the closure of B? What is the closure of B? B determines B, A. B determins A, and AB determines D. AB is here, so B determines D. Now this is BAD or ADB. Now after removing this B determines A, now we are going to find out B plus. B plus, that means B plus include B, and on the left hand side nothing is there, which is the subset of B. That means B plus is B after removing this. So you cannot remove this. B determines A is in the minimal cover. Now we are going to find out D plus. D plus, that means D is there, A. D determines A is there. So only DA. D determines A, and subset of DA is not here, D, and D determines A. Okay. Now after removing this D determines A, you are going to find out D plus, which include D. You have removed this D determines A, and now there is no possibility for another attribute to be included in the closure. So D plus is D only. That means this also cannot be removed. This also cannot be removed. Now what about AB plus? AB plus, is it that includes AB, then B determines A, that is there. AB determines D, ABD. That means all attributes are there in the closure of AB. Now after removing this AB determines D, again you are going to find out the closure of AB. That means you have removed this. AB include AB. Here B determines A, that's already there. There is no D, and AB plus is AB only. So again this can be removed. Okay. Now there is one more thing. That means this the second stage is over. Now you have to check whether you have to search for functional dependencies which is having more than one attribute on the left hand side, and if we have only one functional dependency, AB determines D, Now we are going to check whether this A or B can be removed from this set. Okay. Now, what is AB plus? AB plus is ABD, that we already know. AB plus is ABD. And after removing this A, the closure of B you are going to find out. Closure of B is B, B determines A, B determines A, and AB determines D. That means ABD. That means here ABD. Here B plus means BAD. This is ABD. That means the closure of B connects B and B, A and D. So this can be removed. This can be removed. So the set of productions becomes B determines A, D determines A, and B determines D. Okay. Now see there. B determines A, D determines A, and B determines D. Here B determines D is there and D determines A is there. Then B determines D and D determines A implies B determines A. That means these together implies this. That means B determines C and D determines A implies B determines A by transitivity rule. That means if you have productions B determines D and D determines A, then by transitivity B determines A. So when you are simplifying this, this can also be deleted or eliminated from the list. So the minimal cover is this one.